Hello, and welcome to the next video in the EOS on ADC Precision Lab series. Different types of data converters use different types of internal ESD protection. The most common type of internal ESD protection for ADC inputs is an ESD diode connected from the inputs to the positive and negative supplies. This video will cover the selection of external components to protect ADC inputs from overstress events. Let's start by looking at the data converter specifications. The absolute maximum ratings represent the maximum voltage and current levels that can be applied without damaging the device. In general, your design should have a reasonable safety margin that prevents the device pins from meeting or exceeding the absolute maximum ratings. For example, if the absolute maximum supply voltage is 7 volts and the normal operating supply is 5 volts, you should try to design your fault protection circuit so that the worst case voltage that can be supplied to the power supply is slightly less than 7 volts. In some cases, exceeding the absolute maximum rating momentarily may not cause catastrophic damage to the device, but will damage the device and result in degraded performance. Additionally, notice that the absolute maximum rating is going to be outside the linear operating range. For example, if the linear input range is 0 volts to 5 volts, the absolute maximum rating may be negative 0.3 volts to 5.3 volts. Pushing the device to the absolute maximum ratings not only results in degraded performance as a result of being outside the linear region, but puts the device in danger of being damaged as well. As a reminder, the input should be protected so that EOS does not cause the device to exceed the absolute maximum ratings. This slide shows the absolute maximum ratings for the ADS8860 and ADS9224R. The reason that the input absolute maximum ratings are different is that the ESD diodes are connected to the voltage reference for the ADS8860 and to the analog power supply for the ADS9224R. In both cases, the ESD diodes for negative signals are connected to ground, which is why the minimum ratings are the same. The absolute maximum ratings are typically 0.3 volts above the positive supply or reference and 0.3 volts below ground because the ESD diodes will remain off as long as the forward voltage doesn't exceed 0.3 volts. This 0.3 volts varies over process and temperature. For some devices, the absolute maximum will use a slightly different factor such as 0.4 volts. Now we'll focus on the absolute maximum rating for input current. For most devices, this limit is given as plus minus 10 milliamps. As with all maximum limits, it is generally a good idea to limit the current to be less than 10 milliamps for design margin. One very simple approach to meeting this limit is to use a series current limiting resistor. We will cover the details for selecting this resistor later in the presentation. In general, choosing a large series resistor can make the device safer and reduce the chances of a latch-up event. However, it may affect signal settling for switched capacitor input ADCs. This slide illustrates a typical amplifier drive circuit for a SAR ADC. Part of designing this drive circuit is to select the amplifier bandwidth in the RC charge bucket circuit. The SAR ADC Input Driver Design Precision Lab series covers the method for choosing the drive circuit components for best performance. In summary, the RC circuit and the amplifier bandwidth are selected to assure that the voltage on the internal sample and hold capacitor is settled to 1/2 of 1 LSB by the end of the acquisition period. Generally, the input amplifier supply voltage range is selected to match the input range of the ADC. So if the ADC input range is 0 volts to 5 volts, then the amplifier should use a single 5 volt supply and ground. In some cases, however, it may be necessary to use an amplifier with higher supply voltages. As shown on the slide, for example, the high voltage amplifier may have a special characteristic such as ultra-low noise or distortion that is not available in a single supply amplifier. The problem that arises with this kind of system is making sure that the input voltage of the ADC does not exceed the maximum ratings. In the next few slides, we will cover the component selection for an example design and explain the details of an example protection scheme. This is the TINA SPI circuit that we will use to simulate the input switching behavior of the ADS8860 SAR ADC and the drive characteristics of the OPA828 amplifier. The ADC Precision Lab training series has an entire section that covers this kind of simulation. We will show the measured results for this circuit later on. Right now we aren't looking at the input protection circuit, we are only confirming that the amplifier has sufficient bandwidth and that the RC filter is properly tuned to achieve adequate settling. To do this, we will use the TinaSpice parameter sweep on the resistors in the RC circuit and look at the settling error on the sample and hold circuit. This slide shows the sample and hold error with different resistors in the external RC circuit. The goal is to choose a resistor that gives the lowest settling error at the end of the acquisition period. The end of the acquisition period is marked with the A cursor, and the legend shows the different errors at this time. The half LSB error target is 38 microvolts for this design. Inspecting the curves, you can see that 5 ohms should not be used because it shows overshoot. The settling error for all of the resistances from 7.5 ohms to 15 ohms are less than the error target, so any of these resistors would work. Your initial reaction may be to select the 7.5 ohm resistor as it has the best settling error without overshoot. However, in this case we select 15 ohms as it meets the error criteria and also is the most effective at limiting the current. This slide shows the measured result for the circuit we just simulated. According to the ADS8860 datasheet, the typical SNR is 93 dB and the THD is negative 108 dB. The measured results for the circuit we just simulated are better than the typical specifications. In general, the goal is for the input drive amplifier to add minimal noise and distortion so that the system will be limited by the ADC performance. The next step of this design is to add the protection circuit and confirm that it has minimal impact on performance. As you can see on the slide, we've added the protection components between the amplifier and the ADC. It is important to remember that this protection circuitry is only required because the amplifier has plus-minus 12 volt supplies and the ADC has a negative 0.3 volt to 5.3 volt absolute maximum input voltage rating. This circuit has two different types of protection circuits in it. First, the internal ESD diodes help to protect against the electrical overstress as long as the input current I2 is limited to be less than the absolute maximum rating of plus-minus 10 milliamps. The resistor R-filter will limit this current. Strictly speaking, these diodes will not turn on until the absolute maximum voltage rating of 5.3 volts has been exceeded. However, exceeding this voltage rating by a small amount is generally not an issue as long as the input current is limited to be less than plus-minus 10 milliamps. Notice that a TVS clamp may be required on the voltage reference as the reference may not be able to sink the transient fault current that feeds through the ESD diode. The second layer of protection is the external diodes D1, D2, and the current limiting resistor RP. When the output of the amplifier swings to plus-minus 12 volts, these diodes will turn on and limit the voltage to approximately 5.3 volts when D1 is turned on, and approximately negative 0.3 volts when D2 is turned on. The exact limiting voltage depends on the forward drop of diode D1 and D2. Schottky diodes are normally selected for this kind of protection scheme as they have a low forward voltage drop of approximately 0.3 volts. The resistor RP limits the current flow into the diodes to prevent damage and also to minimize the forward voltage drop. In the next slide, we will go into more detail on selecting the diodes and external resistors for effective protection and minimal impact on performance. This slide steps through all the operating conditions for this circuit. First is the normal operating condition. This is the case where the amplifier output signal ranges from 0 volts to 5 volts. When the amplifier's output is greater than 5 volts, diode D1 will turn on. Alternatively, when the amplifier's output is less than 0 volts, diode D2 will turn on. Technically, diodes D1 and D2 will not turn on until the forward voltage exceeds the forward voltage threshold, so at about 5.3 volts and negative 0.3 volts respectively for a Schottky diode. Resistor RP will limit the current flowing into these diodes during a fault event, and depending on the value of RP selected, the power dissipation in the amplifier and the resistor RP can be significant. Later on we will cover the calculations for the component values used in this circuit. As mentioned before, the diode voltage VD is approximately 0.3 volts for a Schottky diode. However, depending on the magnitude of the current flowing through the diode, this voltage will change. For example, if current I3 is large, then the diode voltage drop will increase. Keeping VD below 0.3 volts will help keep VB and VC below 5.3 volts. If VC is kept below 5.3 volts, then the internal ESD diode will not turn on and we will not violate the absolute maximum voltage specifications. If VB increases beyond 5.3 volts, then the ESD diode will turn on, and this is where it is important to choose an R-filter resistor that will keep the input current below 10 milliamps. With all of these limitations in mind, the obvious solution is to select large values for RP and R-filter to protect the device. Unfortunately, this has a significant impact on the settling of the internal sample and hold capacitor. In short, a large value of RP and R-filter will require a longer time to charge the internal sample and hold capacitor, and as a result a slower conversion rate. Another impact to performance is the distortion caused by the nonlinear capacitance associated with Schottky diodes. Finally, the leakage current associated with the diodes can introduce an offset error. Now, let's take a look at the math behind selecting component values. In this slide, we will cover the math behind the component selection for this circuit. First, let's take a look at the known parameters. Under a fault condition, the amplifier will output nearly 12 volts, which will turn on diode D1 and drive a large current out of the amplifier. The largest output current is limited by the short circuit protection on the amplifier. For the OPA 828, the short circuit current limit is specified as 50 milliamps. Also, the absolute maximum specifications on the ADS 8860 state that the absolute maximum input ratings are at negative 0.3 volts and positive 5.3 volts, and the input current limits are plus minus 10 milliamps. Using this information, let's select a few components. Up to this point, we have assumed that the diode voltage drop was 0.3 volts for a Schottky diode. As mentioned previously, the magnitude of this drop is dependent on the forward current. Under a fault condition, the current through the Schottky diode is the 50 milliamp short circuit current from the amplifier minus any current flowing into the ADC. The worst case voltage drop for the diode happens when the entire 50 milliamps from the amplifier flows into the diode. The BAT54 diode used in this example develops a 0.42 volt drop at 50 milliamps. We will show how to use the diode curves on the next slide to determine the diode voltage drop based on its forward current. For this circuit, a plus 12 volt amplifier output will be limited at VB to 5.42 volts and a negative 12 volt output will be limited to negative 4.2 volts. The largest voltage across RP occurs when the output is at negative 12 volts. Let's use this condition in the 50 milliamp current limit to choose the value for RP. Dividing the resistor voltage by the 50 milliamp short circuit limit sets the minimum value of RP to 232 ohms. Similarly, we calculate R-filter to limit the ADC input current to be less than 10 milliamps. Since the voltage drop across R-filter is relatively small, a minimum resistance of 12 ohms is sufficient to limit the ADC input current. For the final step, we round the resistor values up to standard values. Now let's take a closer look at the diode curves. Here is a selection of several different diodes. Let's look at all the parameters and decide which diode works best for this application. First and foremost, this application requires that we never exceed the reverse breakdown voltage. Since the amplifier supplies are plus minus 12 volts, the maximum reverse voltage applied to the diodes can be as large as 12 volts. A good rule of thumb is to make sure that the reverse breakdown rating is at least twice the applied reverse voltage, or greater than 24 volts in this case. For forward voltage, we ideally want the lowest drop possible. We also want low leakage current, as leakage current will translate into an offset voltage error when it flows through the source impedance. We also want low capacitance, as the capacitance is nonlinear and will introduce distortion. Finally, we need to make sure that the diode can support the maximum forward current, which is the 50 milliamp short circuit current from the amplifier in this example. When you take all of these factors into consideration, the BAT54 is the best choice. Once you have selected your diode, you will need to use the forward current versus voltage curve to identify the diode drop under fault conditions. You may remember from the component selection section that the amplifier short circuit current was 50 milliamps. Assuming the worst case scenario of all the current flowing through the diode, You can use the curves to determine the forward voltage under the fault condition. One thing to notice here is that the different diode manufacturers may have slightly different specifications for the same device. Here we look at the BAT54 from two different manufacturers. Notice that the forward drop specifications from the Diode Inc. manufacturer are slightly better than the ST device under the same test conditions. For this reference design, the 0.42 voltage drop from the Diodes Inc. diode was used in the component selection calculations. Under normal operating circuit conditions, when the amplifier output is from 0 volts to 5 volts, the Schottky diodes are reversed biased. For example, if the amplifier output is at 0 volts, the diode D1 will have a reverse voltage of 5 volts on it. Using a curve from the diode's datasheet, you can determine that the reverse current is about 60 nanoamps at 25 degrees C for the 5 volt reverse voltage. This current will flow through the 200 ohm series resistance, developing a 12 microvolt offset error. As you can see from this curve, the reverse current will change with temperature and reverse voltage. Under a fault condition, the output current for the amplifier can be significant, so the power dissipation of the amplifier and series resistor can also be high. In the case of the resistor, it is important that the correct power rating is selected so that the resistor is not damaged. The worst case power dissipation in RP occurs when the amplifier output is negative 12 volts. The voltage across RP is the negative 12 volts minus the diode drop of negative 0.42 volts, which results in a negative 11.58 volts for this example. The current through RP is calculated to be about negative 38.6 milliamps, which is less than the short circuit current limit. The power dissipated in the resistor is then calculated to be 371 milliwatts. As a general rule of thumb, it is advisable to double the power specification on the resistor for margin over temperature, so a 1 watt rating would work well for this resistor. Unfortunately, a 1 watt rating is a fairly large and potentially expensive resistor. Later on, we will look at an alternative approach that will mitigate this problem. Before we look at this approach, let's check the measured performance of this circuit using TinaSpice. This is the TinaSpice simulation model for the circuit we just selected the component values for. The goal of this kind of simulation is to confirm that the voltage across the sample and hold capacitor settles to 1/2 LSB by the end of the acquisition period. In this example, we are running the ADS8860 at the full 1 megasample per second sampling rate, and the specified acquisition period of this sampling rate is 290 nanoseconds. The settling target is 1/2 of 1 LSB, which is 38 microvolts for this example. The simulation results show that the settling error is 97 millivolts, which is very poor compared to our 38 microvolt target. The main reason for the poor settling is the large 249 ohm resistor RP. This resistor creates a long time constant for the charging of the sample and hold circuit. Let's look at the measured results. Here are the measured results for the circuit on the previous slide. Notice that many harmonics are created as a result of poor settling. Comparing the measured THD and SNR to the datasheet specifications, you can see the substantial degradation in system performance. This slide emphasizes the problem with the large series resistor. The red curve represents the circuit settling when RP is 0 and the diodes are removed from the circuit. In this case, the amplifier is able to fully charge the internal sample and hold capacitor within the acquisition time period. The green curve represents what happens when RP and the Schottky diodes are added. In this case, the large series resistor does not allow the sample and hold to be fully charged by the end of the acquisition period. One way to solve this problem is to extend the acquisition time. This can be done by reducing the sampling rate. On the next slide, we will look at how doing this will improve the system performance. Here we show the performance of the circuit from the previous slide at different sampling rates. Looking at these graphs, you can see that the THD is more affected by the settling error than the SNR. In order to get full performance for this example, the sampling rate needs to be reduced to 400,000 samples per second. In the next video, we'll look at an innovative solution that minimizes the performance limitations and power dissipation issues that we've been discussing. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content. Question 1. For the circuit below, what is the purpose of the TVS diode on the 5-volt supply for the Schottky diodes? The correct answer is A. The 5-volt supply may not be able to sink the current. The TVS will turn on and limit the voltage for large positive transients. Generally, low dropout regulators, or LDOs, cannot sink current. Question 2. True/false. The internal ESD diodes can be connected to either the analog supply or the digital supply. The answer is B. False. The internal ESD diodes generally will connect to the analog supply, the reference, or ground. Question 3. True/false. Schottky diodes have a better leakage current than a p-in signal diode. The correct answer is B. False. The leakage for Schottky diodes is generally higher than p-in diodes. Question 4. True/false. Schottky diodes have a lower forward voltage than a p-in signal diode. The correct answer is A. True. The forward voltage for a Schottky diode is typically 0.3 volts, whereas the drop for a p-in junction diode is about 0.7 volts. Question 5. For the circuit below, what is the approximate current in the diode ID? The correct answer is C, 10 milliamps. Subtracting the diode drop in the 5-volt supply from the 15-volt amplifier output yields 9.7 volts. 9.7 volts divided by the 1 kilo-ohm resistance is 9.7 milliamps. The best answer is 10 milliamps. Question 6. Continuing with the circuit from the previous slide, what is the forward voltage drop across D1 at 25 degrees C? The correct answer is D, 0.35 volts. From the previous slide, you know that the current is about 10 milliamps. The 25 degrees C curve intersects 10 milliamps at about 0.35 volts. Question 7. Assuming the protection circuit is causing distortion, how can the distortion be reduced? The correct answer is C, decrease the sampling rate. Decreasing the sampling rate will increase the acquisition time. This will allow a longer time for the internal sample and hold capacitor to fully charge or improve the settling. This has the effect of improving THD.